All right, class. So this is an explanation video for the practice quiz question number 6. And this is definitely a more challenging type problem for us at this stage of the game. There's some concepts in here that we haven't explicitly talked about in class, but hopefully we can sort of figure them out and do this problem. So let's go ahead and get into it. So for this problem, we're asked to find the number of individual hydrogen atoms present. So when we think about individual hydrogen atoms, basically what we should really be sort of thinking about is Avogadro's number, dimensional analysis, that sort of stuff. And then we're also given a volume and a density. So for the density of water, it's actually pretty easy because the density of water is 1 gram per milliliter. So for this 353 milliliters, we can convert that essentially pretty quickly into grams. So I'm going to write over here, this equals 1 gram per milliliter. And then we're going to convert that from milliliters to grams in the first step. So for part A, 353 milliliters times 1.00 grams per 1 milliliter. That's going to give me 353 grams. Now, I'm going to show each step sort of individually. You don't necessarily have to do that, but I think it's nice. Now, I'm going to take this 353 grams, and I'm going to convert that into moles of H2O. Now, for those of you who are currently in my class, this is the step that we haven't exactly talked about yet. Some of you might have been able to figure it out, and that's great. But if I want to convert from this mass of H2O, this is my mass of water, into moles of H2O, I'm going to use the molar mass of water. I'm going to add up the molar mass of oxygen and hydrogen, or the atomic masses of oxygen and hydrogen to get to 18.02 grams. Each hydrogen atom is 1.01, and then the oxygen is 16, so add those up, I get 18.02 grams. So this conversion, again, it's really just a unit conversion, is going to get me to my number of moles, 19.589 moles of H2O. Now, like I said, this aspect of this problem, for those of you who are currently in my class, that's a little bit, above where we are currently. But I feel like we should be able to do that. So anyhow, 19.589 moles of water. And now we need to figure out, okay, if this is the number of moles of water I have, how many moles of hydrogen do I have, and how many moles of oxygen do I have? So in the next step, I'm going to take 19.589 moles of H2O, and I'm going to use a ratio of 2 moles of hydrogen atoms per 1 mole of H2O. So basically what I'm saying here is that each water molecule has 2 hydrogen atoms. Another way to think about this is if you think about a bicycle has 2 wheels, right? So if you have 5 bicycles, you should have 10 wheels. This is the same sort of ratio. Each one of these has 2 H's. So if I've got 19.589 moles of water, I'm going to have 2 times that number of actual moles of hydrogen. So equals, and that number is, let's find it here, 39.179 moles of hydrogen. So this is my number of moles of hydrogen to convert to my atoms. So that's part A, individual hydrogen atoms. I'm going to take this number of moles, 39.179 moles of hydrogen times Avogadro's number, 6.022 times 10 to the 23rd atoms of hydrogen divided by 1 mole of hydrogen equals 2.36 times 10 to the 25th individual atoms of hydrogen. So that's my answer for part A. And in part B, we are just going to be doing the same thing for oxygen. So for oxygen, we can go back here to this 19.589 moles. We can start from that point. We could do all the other steps, but we don't really need to, right? We know that we're going to need this 19.589 moles of water. The ratio here is going to be 1 mole of oxygen for every 1 mole of water. So the way I would think about this, right, it's just like that bike example. If you have 5 bicycles, how many seats do you have, right? You've got 5 seats. It's a 1-to-1 ratio. So in my water molecule, the oxygen would be the seat, and the hydrogens would be the wheels. So I would have 2 wheels, 2 hydrogens, 1 seat, 1 oxygen, a 1-to-1 ratio here. So this is going to allow me to convert from moles of actual full molecules 2 moles of seats. How many individual seats do I have? Obviously, that's just going to be 19.589 moles of oxygen atoms. And then we can convert 19.589 moles of oxygen by Avogadro's number times 10 to the 23rd atoms of oxygen, atoms of oxygen over 1 mole should equal 1.18 times 10 to the 25th atoms of oxygen. So that's what I'm looking for this problem. A lot of dimensional analysis, right? And I want to be able to see your units, right? We should be able to go through here, cancel out our units, moles. Oh, yeah, moles. Moles of water here, moles of water here, so on and so forth. I should see that easily in all of the work that you're going to be showing for this problem. All right, hope that explains what I need to explain.